Did you click on this video because I looked like someone who could teach you relativity? I think you have great powers of perception. If you're willing to invest a little bit time in understanding relativity, I promise you, it's amazing when you understand how this world works and how weird, how crazy it is that we live in such a world, such a universe. And if you have no background in math or physics, it's okay. You would understand it. I got you. And it's fun rediscovering the math and the physics. So join me today in talking about the first lecture in this series, which is going to be talking about Galileo's relativity. And then there are three more. The second lecture is something that does not get taught in the way that I'm going to teach you. So in today's lecture, we'll start the story of relativity with Galileo's relativity. And this is the first thing you should know. Relativity was not discovered by Einstein. It was started by Galileo, and the thought is very deep and may be confusing, but it's real. You should know what's the core question that led to this thought. Why did such a major shift have to occur? And that is related to the movement. It's about movement and being at rest. When do you know when you're moving and you're not moving? This is at the core of relativity. But why did we start questioning these things? See, for thousands of years we believed that when you observe the sky and you see the stars rotate, you see the sun and moon rotate, and they have their own cycles. You have the lunar cycle for which is month, which is called a month, does this in a month, sun does this in a year. All of these things, it looks like they are doing this, all of that is moving, and we don't move. Over time it's started becoming clearer and clearer that the theory which suggests that the earth doesn't move and all the heavens move around it has problems, has mathematical ugliness that is done away with more elegantly if we say that the earth went around the sun. That was Copernicus. But then it brought a big question. We would know if we moved, right? Because if I get on a horse and I feel the wind in my face, I know I'm moving. And when I'm in a horse carriage and it starts, I feel the movement. So why would I not feel if I moved 300 kilometers last year in the last year? So this was a major debate in that time. And to answer this question, why, if we actually go around the sun, then we must move this much, and why don't we feel anything? I'm going to take you into a thought experiment. Time check. Okay, because many of my viewers are young and they don't have the patience to go sit through a lecture, so I have to re-record. Okay, so imagine that there's nothing in the world, which is hard to imagine, and then there is a room in the world, and the room, as a man, will call him hombre, and he has a ball and a ruler and also a clock. I was going to make it more general, define what a clock is, but let's say that you have an idea of what a clock is. It measures, never mind, you know what a clock is. But for now, we won't need the clock. He's born in this room with a ball and a ruler, and he can do any experiments he likes, and he has nothing to do, so all he does is experiments. The first he does, that he leaves the ball like this, and the ball stays there. Where else would it go? There's nothing else in the universe, so it has no reason to go anywhere but to stay here. The ball stays here. Then he moves the ball and the ball stays there. So great, the ball doesn't move once you move it from this position, it just remains wherever you put it. So any position is the same as the other. Maybe not, because there is the room and the distance from this wall to this ball and this wall to this ball changes when I move it. If I do this, it comes closer to this wall. If I do this, it comes closer to that wall. So he comes with a system. He starts measuring distances to the wall, and he starts calling them by two numbers because he realizes that he can always measure distance from his head, but then if he measures the distance from his head, he can have any, the ball could be anywhere on the circle and it doesn't fix where the ball is, so he needs two distances. Great. So Now if we imagine that this is the room, the ball is here, then this is y and this is x. If the ball is here, this is x and this is y. So you move the ball anywhere on this board, it for each of the point it would have two numbers that very uniquely correspond to where the ball is. Great. Now he does some other experiments. He throws the ball around. So he pushes the ball goes and it bounces and reaches him again. When it does it faster, harder, the ball does it faster. And he does all kinds of experiments. He throws the ball around, it jumps in. Oh, that looks wrong. So it jumps in the room, etc. And he has figured out the laws of reflection and basically collision and so on. So he now knows his room very well. One day it turns out that there was another room right next to him. And now this is ombre A and ombre B, and it turns out that ombre B has been doing the exact same things that ombre A was doing until then. And now ombre A is a little bit, he's in a little bit pain, because all this time he thought that his room was the main one. His room was the only thing, and now there are two rooms. Which one is the real one? Like, they have all these questions. After a little bit of argument, they realize that both of their rooms are exactly the same. All the things that they can do with the ball, when ombre B leaves the ball here, it remains here. So what that means is the distance that he measures to the ball, the coordinates that he gives to the ball remain the same, and for ombre A as well. So if he leaves the ball here, ombre B measures these as coordinates, but ombre A measures these as coordinates. So the coordinates are different, but they're constant, they're static, they don't move. So the ball doesn't move in either of the cases, except that the coordinates are different. So what they want to do now is to come up with a way that if you have the coordinates measured by B, you should be able to convert them as measured by A, ombre A. And I encourage you to pause the video and figure out how it would work, how it could happen, and I'd give you that the distance between the end points of the room or any two same points of the room is D. So yeah, of course, you get the point. I'll quickly tell you this because the best part about relativity is yet to come. So if there is a ball here and ombre B measures the distance as xb and yb, xb and yb, ombre A would measure the same y, because the room is in the x direction, like it's shifted in the x direction, in the y they're in the same level. So the y distance, this distance is the same, but then there's an additional d distance in this direction. So for xa is equal to xb, which is this distance, plus this d, which is a constant. So the moment they do this, they can do these experiments of reflections and so on, right? And they can measure, ombre B can measure in his frame, and now XA, all XA has to do to find out what XB is measuring is to subtract D. So it would look something like this. And the moment he subtracts D from the X direction, then it's as if the room is the same. It's like shifting this room here. Great. It's as if it's the exact same room there. So neither of them can say that their room is the fundamental room, because he can also shift this room here by adding D. So what that means is that both of these rooms are equivalent points of references, the rooms are the same. But then it's not going to remain easy for them. In this video, we are going to talk about the first challenge they face. Once they look up and they see a whole new room with ombre C in it, the same ball, same ruler, but the room is moving. It just floated like this and it's going away. And this is exciting for them because in their experience, if you leave a ball, both of them measure the same. They measure the distances to the ball and it doesn't change. They measure different distances, but the distance doesn't change. So now what would happen if ombre C let the ball go here? They would expect that the distance wouldn't change. From their perspective, the ball would remain here, and ombre C and his room and everything would move forward like this, and the ball would remain in that place. And this is something, if you ask people, that if you are going on a two-wheeler, on a motorcycle or a scooter, and you are sitting in the back seat, you throw a ball up, should the ball drop in your hand or not? people People say that, a lot of people say that it would not drop in the hand, but rather, if this is the scooter, imagine that this is a scooter, and they throw the ball up like this, they think that the scooter will move forward. This time I will draw a better scooter, and then the ball should drop here and it should fall on the ground. And you should try this. It doesn't happen. Drops in your hand. And it's better seen if you're in a bus and you throw a ball. It doesn't hit you in the face and fly through the windshield, back shield, right? Back window. Doesn't. It falls on the ground as if the bus were not moving. So if the bus were not moving and you drop a ball, it falls like this. If the bus is going at a constant, like a very nicely at 200 kilometers per hour, let's say it's going at 70 kilometers per hour, it still drops the exactly the same way. And this is the same thing that happens with Ombre C. They ask him to do the experiment, and the ball remains right where he dropped it, as with respect to him, with respect to his coordinates. But these people are now in problem. It's hurting them because their coordinates are changing. By the way, I ask you to do this exercise. Pause this video and do this exercise. That I said that, okay, this room is right here, it's shifted by distance d, so you subtract d from xa to get the coordinate, like you transform the coordinates. Now if the room was here and shifted by d vertically, how would you do this? How? Okay, try to think of that. Now Omre C's room is moving, and the coordinates of the ball in his room do not change like they don't for him, for these two people. But for these two people, it's everything is constantly changing in that room, or rather only the x, because it's moving in the x direction. So the y distances that they keep measuring to the room are the same, but the x distances are completely, like, constantly increasing. And this is where relativity comes into picture. Ombre C says, wait, what have you been saying? You have been saying that I'm moving, I'm moving. I was born in a room. I did the experiments. I came up with a coordinate system. I look out the window and I see two rooms coming like towards me. You guys are the one who are moving. I have never moved. And this is annoying. This is dangerous. Ombre A and B are thinking, we have been moving the whole time. How did we not know? How much distance have we traveled? That makes no sense. So what these three decide to do is to see whether the physics is different. Whether the ball, if you throw it, whether it comes back harder, like faster, or something like that. If that's the case, then we can say that at least there's a difference between our frames, and it doesn't, like, it's not equivalent. At least one of us has to be moving if there is a difference. So yes, but the first task that they have to do is to transform the coordinates so that, because see, this is Ombre C's room and this is Ombre A's room. In this case, they are aligned, so no difference in y. In the previous case, all we had to do was subtract d from Ombre A's distances to get Ombre B's distances. So it used to be xa minus d equal to xb and ya equal to yb, right? But now this distance between the far ends of the room is constantly increasing. So you can't just subtract a constant. What would you like to subtract instead? So now they realize that they had the clock again. And they see that if you measure the distance, because they have the laser measurer, remember, if you measure the distance it takes, the entire Ombre C's room travels in 10 seconds, and then you measure it for 20 seconds, you realize that it travels twice the distance in twice the time. So because Ombre C's room is moving uniformly, so it's proportional to the time. The more the time, the distance increases. And see, remember, the goal is that you have the distances measured by Ombre A and you want to convert them to the distances measured by Ombre C of the same ball. In Ombre A's view, the ball is constantly moving, so Ombre C has to constantly subtract a bigger and bigger distance, and so time is something that constantly increases. That's by one of its properties. So v is the speed by which, so the room could be moving faster or it could be moving very slow, and this term will constantly increase. But this term will ensure that xa also increase, vt also increase, but xb remains constant because ombre, sorry, now this is xc. Ombre c always measures the same distance. So this distance would come out constant. So all xa has to do to find out the distances measured by xc is to subtract this constantly increasing term vt from all the distances that he measures in the x direction, because this is moving in the x direction. Please work out what would happen if the room was moving like this. Right, and when they do this, when xa, so okay, the first of all, when ombre c moves from here to here, and he pushes the ball down like this, what he sees in his frame is the ball does this, but what ombre a sees is the ball does this. These are two different trajectories, two different distances traveled, but what ombre a can do is subtract vt, and then ya is constant, vt from xa, and then he would also get, so you subtract vt from this distance at each time. Okay, here time was 1 second, 2 second, 3 second, and so on. So all of these points would jump to these points because you're subtracting a proportionally growing term out of it. So this line would do this the moment you do this. So when he does this linear change, he realizes that he gets the same results. It's as if ombre c's room is exactly the same as him, only the difference is that this term. But the moment you have this, then the physics, all that, like the moment you keep subtracting this increasing vt term, all the physics and everything looks exactly the same. And ombre c can do the same. And the fact is that ombre c never thinks that the ball did this at all. He thinks that ombre a moved back with his ruler. Ombre a is the one who has been moving and he never moved, and he can do the same. And in his case, he will just have to do a plus uh, in his frame. So you see, both of them can say that they are the one who is moving and the other one who is not moving. Oh, sorry, they are the one who is not moving and the other one is moving, or they can say vice versa. And neither of them would be right or wrong for that matter. And this is the essence of relativity. Moving with the same speed, okay, essence of Galileo's relativity, moving with the same speed is like not moving at all. Here, is this chalk moving? Most of you would be saying that yes, it's going around the sun. And yes, in the last 10 seconds that I've been talking, this chalk has moved 500 kilometers with respect to, I don't know, some star far away. So this chalk, is it moving or is it not moving? And the answer is, thanks to Galileo, I can say that to me it's not moving, and nobody can say otherwise. But then again, the question of feeling movement, we feel movement when the car starts and we feel this back movement, when we are on this children's rotating toy that they have in the playground, we feel this outward force. So we know when you're rotating, we know when we're moving, but then it turns out that we don't feel the speed at all. As I told you, if there are these bullet trains in China, and you cannot tell if it's going at 2 kilometers per hour, 200, 300 kilometers per hour sitting still. That smooth maglev trains. And you can do any experiment, you can do balls and jump, like juggle balls, it looks exactly the same as if you're not moving. So if you're juggling a ball, in your view the balls are doing this, but for someone who is not, like who is on the ground, the balls would do this, and all you have to do is subtract that vt and then you would get this again. Now as respect to why don't we feel like we're moving around the earth, first Galileo asks us to imagine these inertial frames. The rooms are inertial frames, and he says that these are when there is no external influence, so in deep space where there is no gravity, etc. So but we don't live in deep space, we live right next to a very massive object that is the sun, and we go around it. So we should feel like we are like thrown away a little bit, right? And the reason is that why we don't feel it is, in most of the cases you see this circle, but if this is this earth, and then the orbit of the earth would look like this. The circle is so big it would look like a line. So earth is going like this right now with 50 kilometers per hour. But with respect to what is something you should ask, and I would not get into it right now. It's a huge topic. So Earth's speed is not really changing. It's very slightly tilting in this direction if sun is in that direction, and that is why you don't feel it. But you can measure it in the laboratory. And if you stood on the that rotating merry-go-round thing on the playground, and you rotate, like someone rotated it in a speed that it would rotate once in one day, one in 24 hours, you wouldn't feel that too. I mean, it, because we don't have the senses that are so precise. Otherwise, physically the difference exists. And why it exists, why we can measure acceleration absolutely but not speeds, is something that I can't get into into the video right now. Probably we don't know yet very well. Okay, so that's Galileo's relativity. The next topic is photobramic relativity, something you might not have, okay, you absolutely have not heard of it because I made up that word. Because before Einstein's relativity and after Galileo's relativity, there's this middle section relativity which gets jumped over in every physics textbook because it happened so fast. But I want to talk about it because without it, it wouldn't make sense. You just have to mug up the formulas for Einstein's relativity. I'm going to continue this thought experiment, and I would like to meet you in the next video. Thank you for watching, and shout out to Luigi Mangione. That guy has heart.